The white hole, one of the strangest objects in the universe.
Black holes are weird, but white holes, they're way weirder.
Science predicts they should exist. But these astronomical wonders are so mysterious, no one is sure what they really are.
How do you start looking for something that you have no idea what it might possibly look like?
Today, astronomers race to find the clues that can unlock the secrets of white holes. Can unexplained energy bursts deep in space be a sign of these enigmatic objects?
To this day, we still don't know what caused it.
And could a white hole be a gateway to a different time and space?
White holes sound like pure science fiction, but they could be science reality.
We venture to the farthest reaches of the universe. Go back in time to the moment of its creation and journey through the monster at the center of our galaxy to hunt for the truth about white holes. Our universe is home to a mind-boggling array of mysterious objects. Stars so magnetic that they rip apart atoms. Planets where diamonds fall as rain into oceans of liquid hydrogen. Threads of dark matter, billions of light years long, that weave the entire universe into a vast cosmic web. Astronomers have unlocked many of the secrets of these weird cosmic creations. But one theoretical object in the vastness of our cosmos confounds the greatest minds in science. It's called the white hole. A white hole is a super powerful stream of energy that pours from an intensely bright point in space. It emits radiation so powerful that nothing can venture near.
A white hole certainly has to be one of the most mysterious objects that the universe could possibly conjure up. But you wouldn't want to get too close. I think if one went off anywhere near in our galaxy and it was pointed at us, you wouldn't even know it was coming. The Earth would be fried by the light coming out in an instant.
No astronomer has ever seen a white hole. Does this galactic monster really exist? A clue lies inside the brilliant mind of the world's most famous physicist.
Einstein is truly a cultural icon. If somebody said the word genius to you, one of the first things you might think of is the face of Albert Einstein, his crazy hair and all that. But all of that overshadows just what a profound effect he had on modern science.
Over a century ago, Einstein comes up with a theory that changes everything we know about the universe.
Einstein's general theory of relativity tells us that the universe is not as it seems. It puts limits on what we can do in space and time, how fast we can travel. It basically affects everything we understand about the universe itself.
Einstein's theory stretches space, literally, and predicts the existence of one of the strangest objects in the universe. General relativity combines space and time into space-time, the fabric of the cosmos, which is flexible. Extremely heavy objects can actually warp space-time to create gravity wells around them. The more massive the object, the bigger and deeper the gravity well. But the theory predicts one object that could stretch space-time to its limit, a point so dense that nothing escapes its thrall. The name for this bottomless gravity well is a black hole. It is an object that transforms physicists' ideas of what's possible in the universe. Einstein's theory also predicts another mind-bending object.
The equations of general relativity allow us to push the limits of the universe as far as we can. What if there's something that's like the opposite of a black hole, a white hole? Well, the mathematics of general relativity allow for that as well.
Einstein's equations make it possible for white holes to exist. How would they work? Clues to how they might operate could lie in the extreme physics of their theoretical opposite. A black hole. In the 100 years that follow Einstein's theory, definitive proof of a black hole's existence, a photograph, eludes astronomers.
Up until now, really what we've had is indirect evidence. Wouldn't it be amazing to actually see the black heart of it itself?
How can astronomers see a black hole to take a picture of it? Fortunately, Einstein's theories predict that black holes and white holes both share a common feature.
Out of these complex theories come these mathematical predictions that sound like science fiction, but in reality, they give us actual things to search for in the universe. One of those science fiction sounding ideas is something called the event horizon, this purely mathematical boundary that is the prediction from the theory. And yet, this is an actual physical surface that we can search for.
The event horizon of a black hole is the invisible boundary beyond which nothing, not even light, can escape. In theory, it should leave a mark that astronomers can see.
As matter falls into a black hole, it gets superheated. And when it gets superheated, it glows and it gives off light. So we can find it.
If this direct evidence for the existence of black holes is out there in space, then it is possible to unlock what makes black holes tick and use this information to unravel how white holes work. Photographing a black hole is a huge challenge.
The strength of a black hole doesn't come from its size, it comes from its density. You actually want to compress as much matter as possible into a very, very small volume of space. And what happens is that makes black holes very small, and that makes them hard to see. And in fact, even the biggest black holes, if you want to see them, you're going to need a telescope the size of the Earth.
In 2017, 8 radio telescopes across the globe joined forces to take a first picture. From Arizona to Hawaii to Europe, even the South Pole, all aim at the exact same spot. The heart of a galaxy 55 million light years away. This is the picture that the telescope captures. The first ever photograph of a black hole.
This image just makes my jaw drop. It's not some myth, it's not some story. It's real data.
Now that we have this image, that's it. How can you be a black hole denier? That would be as crazy as saying the Earth is flat.
The image proves that black holes exist. It also reveals how the event horizon of a black hole works. And this is the first step to unlocking how a white hole operates.
That circle is actually from a disk of material swirling around the black hole. Any light inside of that region circles around the black hole a few times and then falls in. So it actually can't escape to reach our telescope, and it looks dark.
The photograph shows that the event horizon really is the point of no return for both energy and matter. What does reverse engineering the event horizon of a black hole tell us about how their theoretical opposite, a white hole, works? And could an unexplained burst of energy lead astronomers to the first ever sighting of a white hole? Astronomers are on the hunt for the most elusive object in the cosmos. The white hole. Einstein's theory of general relativity predicts that it can exist. Can reverse engineering its twin, the black hole, reveal how a white hole works? Physicists believe that a simple stream of water unlocks the mystery of how a white hole behaves.
It turns out that you can demonstrate the rough behavior of a white hole in your kitchen sink. So if a black hole is a region of the universe that something can only ever enter and never leave, a white hole is the opposite of that. It's a region that something can only ever leave and nothing can ever enter.
The falling water makes a circle of fast-moving liquid when it hits the plate. Outside is an area of slow-moving water. The boundary acts like the event horizon of a white hole.
It creates this continuous, outward-flowing cascade of water that serves as a kind of barrier for anything trying to enter.
Energy or matter from inside the white hole gets flung out. Energy or matter outside the event horizon can never enter the white hole.
It just can't. There's this outward-flowing barrier of water that's preventing it from doing so.
Flipping the physics of black holes 180 degrees unlocks how a white hole should work. What would this look like in the depths of space? A black hole's immense gravity draws in everything that gets too close. As a planet approaches the dark sphere of the event horizon, it stretches out and disintegrates. Once inside, it's a one-way trip towards the black hole's infinitely dense heart. A white hole works in the opposite way. Energy and matter accelerate outwards from its center. Once outside the event horizon, nothing can return. The science of white holes works, but finding one in space is a big challenge.
The problem with white holes is the equations allow for a lot of different conditions for these things, and so we can look all over the sky, but we don't really know what we're looking for. If white holes exist, they might last a long time or a short time. They might give off one kind of light versus another kind of light. All of these things, all of these variables make them very hard to search for.
Where might white holes be hiding in the universe? What are the signs that will help us find them? Astronomers believe that tracing the energy a white hole shoots out into space could pinpoint its position. And it's possible that we might have already seen one. In June 2006, the Swift Space Telescope detects a massive release of energy in a distant galaxy around 2 billion light-years away. It is a super intense beam of radiation called a gamma-ray burst.
Gamma-ray bursts are some of the most extreme and luminous events in the universe. They are hyper-energetic. The amount of energy that these events liberate is extraordinarily high.
The gamma-ray burst that Swift sees lasts over 100 seconds. A burst this long likely comes from gamma rays released by a star going supernova. NASA tasked the Hubble Space Telescope to search for the aftermath of this probable stellar explosion. Hubble spends weeks hunting for the telltale glow of light that a supernova always produces after the initial gamma-ray burst. But Hubble finds no such glow.
When we followed up and looked at this galaxy, there wasn't anything there. There was no supernova associated with it.
It's as if the gamma-ray burst appeared from nowhere. To this day, no one knows for sure what created it. But one object could, in theory, be able to blast into existence, release a vast amount of energy, and then simply vanish. An explosion of light appears from seemingly nothing. Twin beams of intense gamma radiation, traveling at almost the speed of light, shoot out across space. The gamma ray burst, turning down the brightness on this cosmic light show, reveals the possible source of the fireworks. A perfectly spherical ball spewing out so much energy that nothing can enter it, not even light. A white hole. The Swift Space Telescope spots a number of similar unexplained blasts over the next 15 years. Are these the signs that astronomers searching for white holes are looking for?
Since 2006, there have been several gamma-ray bursts that aren't really well explained by the standard models out there. Perhaps they could be the long-sought white holes.
A single gamma-ray burst releases more energy in 10 seconds than our sun will emit in 10 billion years. If this mysterious gamma-ray burst is from a white hole, where does this energy come from? And how does it get inside the white hole in the first place? Unexplained mega blast of radiation could be evidence of elusive white holes. How this energy gets inside them in the first place puzzles scientists. Can unraveling this mystery help astronomers pinpoint the location of a real-world white hole? The solution to this puzzle may lie inside the super-dense heart of the white hole's twin, the black hole. Black holes are so dense and warp space so much, they work like cosmic car crushers. Matter falling in first gets stretched, then so extremely compressed, it almost ceases to exist. Einstein's theories predict that inside a black hole, matter squashes to an infinitely hot, small, and dense point. But the problem with infinity is that what works in theory may not work in practice.
It's one thing to mathematically express infinity. It's another thing to realize infinity in our actual universe. And there has been no observations of an actual infinite density of anything.
Physicists are now evolving Einstein's theories to explore what really happens inside a black hole. These new ideas put a limit on how small and how dense the heart of a black hole can get. And that limit could unlock where the energy pouring out from a white hole comes from.
Well, the idea now is that there is a smallest amount of volume in space. You cannot get any less than that. It's not zero, very tiny, but it's not zero. That's like a brick wall. When that black hole collapses down and hits that volume, it basically has to stop.
One radical theory explains what that brick wall is and what it is made from. Inside the nucleus of every atom are two types of particles: protons and neutrons. Inside these subatomic particles are even smaller entities called quarks. Some scientists believe if we could peer deeper, we would find the fundamental building blocks of both matter and space: tiny quantum loops. These are the threads that weave together the fabric of the universe. These quantum loops are the building blocks of more than just matter and energy. They make up space itself. The theory says that it is impossible to compress anything smaller than the size of the loops. That means the loops put a limit on how dense a black hole's heart can get. This idea could unlock the mystery of where the energy blasting out from a white hole comes from. It's likely that there is no infinitely small point at the center of a black hole. Instead, there could be a ball of super dense matter. It contains everything that the black hole has swallowed in its lifetime. Eventually, this ball reaches a point where it can contract no further, and so it goes into reverse. It releases matter and energy, swallowing up its event horizon. What was once a black hole has bounced into a white hole. The theory of quantum loops unlocks where the energy blasting from a white hole comes from and how it got inside in the first place. It states that a white hole is one stage in the evolution of a black hole.
If everything in this theory adds up, then what this means is a collapsing and bouncing black hole could be a path to a white hole.
It is possible that bouncing black holes unleash the mysterious gamma-ray bursts that astronomers detect. But what type of black hole could we actually see live as it transforms into a white hole? And where in the sky should astronomers point their telescopes to capture the moment of eruption? Astronomers are on the hunt for elusive white holes. One theory states that they release vast amounts of energy when a quirk of quantum physics throws black holes into reverse. This change is called a bounce. No astronomer has ever seen this dramatic transformation. Where should we point our telescopes to witness it live?
If we're going to look for black holes that are becoming white holes, then we have to look in the right places and for the right things. Space is big, it's huge. So this is very important if we're going to find these things.
Most of the black holes in our galaxy are stellar black holes. Each one weighs around 10 times more than our sun. A stellar black hole forms when a star dies. It leaves behind its super dense core after it goes supernova. This core collapses under its own extreme gravity. This gravity well is so large that it eventually turns into a black hole. Our Milky Way contains around 100 million stellar black holes. In theory, seeing one bounce into a white hole is just a matter of time.
If there's this idea that black holes do eventually come to the end of their lives and turn into white holes, couldn't we just wait for that to happen? There are black holes all around us.
But there's a problem with waiting for stellar black holes to turn into white holes. The transformation could take so long that it will probably never happen.
We as flesh and blood human beings on our tiny little planet Earth think of time as some constant force, but it's actually not. One of the fundamental tenets of general and special relativity is that time and space are fundamentally the same thing. And because black holes warp the fabric of space-time so much, they do really crazy things with time. So in a way, observing anything close to a black hole is like watching time in really, really slow motion. And so a black hole could in principle take trillions of years to evolve in any real way.
The Milky Way is around 13.6 billion years old. The rules of relativity mean that the stellar black holes in our galaxy are too large and too young to bounce into white holes. The telescopes on Earth could watch the black holes in the Milky Way for billions of years and never see one collapse into a white hole.
When we think of a black hole, and we think of one that's like 10 times the mass of the sun, a sort of a typical stellar mass black hole, that takes far longer than the age of the universe for this thing to rebound.
Astronomers think that black holes must be very small and very old to even stand a chance of bouncing into white holes. Where in the cosmos can they find them? A clue could lie in the images taken by the Spitzer Space Telescope that studies some of the oldest objects in existence. Spitzer takes this image of a portion of the universe. It shows a 1 degree wide strip of the sky and the Great Bear constellation. This tiny sliver of space contains 50,000 visible galaxies. The image offers a possible glimpse of objects that could bounce into white holes. To see extremely far back in time, astronomers must first remove all the bright points of light that come from closer stars and galaxies. The technique leaves behind this, a background infrared glow coming from the ancient cosmos. The glow comes from something very old and very distant. What is emitting this huge amount of infrared energy? Another space telescope could unlock the mystery. The Chandra telescope sees the universe in X-rays. X-rays sit at the opposite end of the light spectrum to infrared. They reveal the hidden light coming from superviolent events like supernovae. Astronomers direct Chandra's X-ray camera to the exact same patch of sky as Spitzer. It shows that the ancient universe also has an uneven X-ray glow. Astronomers use computers to compare the two images from the two telescopes. They make an extraordinary discovery. 20% of the bright patches of infrared light match up with bright patches of X-rays.
Way, way down, deep in the noise, you need a computer to pull out the statistics. There's a correlation between this background glow in the X-rays and infrared, and that's very mysterious. No object should be able to glow in both those types of light brightly at once.
Astronomers believe that there is one object in the early universe that could glow in this way.
Remember, we're looking eons back in time here at some of the earliest moments of our universe. And we're seeing objects that are emitting a huge amount of energy across the electromagnetic spectrum. And what's the kind of object that could do that? It's a black hole.
The telescopes see back in time to before stars were even born. How is it possible for black holes to exist if there were no dying stars to make them? And could white holes be the missing ingredient of theoretical tunnels through time and space? White holes are cosmic oddballs born from Einstein's theory of relativity. One idea is that a white hole is the last gasp of a dying black hole. A burst of energy released in one giant cosmic belch. But the only black holes ancient enough to bounce like this date from when the universe contained only energy. How is it possible for them to exist if there were no dying stars to make them?
We know that black holes take an unimaginable amount of gravitational power to make, and the only way we know how to make that is an exploding star. But is it possible the universe had another way to make black holes? Something that only existed in conditions just after the Big Bang.
The Big Bang unleashes forces so powerful they could, in theory, bend space and time enough to make small black holes. Milliseconds after the Big Bang, the universe is a tangled web of pure energy. Superdense pools of this energy condense and collapse under their own gravity to rip deep wells in space-time. These primordial black holes are born small. They mature and shrink further over billions of years. In theory, many could now be old enough and dense enough to bounce into white holes, just in time for us to spot them.
So this type of black hole is really, really small. And because it's so small, we might be in this sort of Goldilocks zone in our history of the universe, in which just enough time has passed for us actually to be observing this transformation now.
A tiny primordial black hole could be astronomers' ticket to witnessing the birth of a white hole. But is there something even weirder out there waiting to be discovered? Einstein's theory of relativity predicts a mind-blowing link between black and white holes. A tunnel to a different place and time, known as a wormhole.
What Einstein showed us when he invented general relativity is that space is not just this background against which everything takes place. Space is a part of the game. It expands, it contracts, it warps, it waves, and it can actually have tunnels.
A wormhole might sound like science fiction, but in theory, a shortcut through space and time isn't a great leap in the upside-down world of white and black holes. Matter and light cross the event horizon of a black hole. The extreme gravity inside stretches space into a funnel. It is theoretically possible for something that survives the crushing gravity to pass through a wormhole and emerge from a white hole in a different part of the universe.
You have a black hole on one side and a white hole on the other. Now, it sounds crazy because you can enter a black hole at some place or time and exit the white hole at another place and time.
But Einstein's theory states that a wormhole only works as a closed system.
The problem is when you look at the mathematics of how a wormhole exists, they're unstable. If even a single atom of hydrogen enters one, they collapse.
A tunnel between a black hole and a white hole must be fed an exotic form of matter to stay open. Humans will need to generate this weird material to stop a traversable wormhole from collapsing.
In order to make them stable, you'd have to have some sort of matter that actually has a negative energy. And I don't think we even really understand what that means. So while Einstein's theories led to the idea that you could build these bridges, how exactly they would stay open is still a complete mystery.
But when Einstein speaks, astronomers listen. How can scientists find a wormhole in deep space? And is it possible that one exists in our own galaxy? Astronomers hunt for a wormhole, a theoretical tunnel between a black and white hole that traverses space and time. Their quest begins with the black hole that they believe lies at the heart of our own galaxy, Sagittarius A star. Every year, the European Southern Observatory in Chile takes a photograph of the same spot at the center of the Milky Way. The data from 16 years of observations creates this 4-second time lapse. It shows stars 26,000 light years away from Earth, circling the heart of our galaxy. But what they orbit appears completely invisible.
You can see these stars, and they're moving around nothing. You look to the center where these stars are orbiting around, and there's nothing there. There has to be mass there because it's telling these stars how to move in this really, really well-defined orbit, but there's nothing there.
Astronomers believe that only a giant black hole has enough mass for stars to orbit in this way. One theory states that charting the orbit of one of these stars could reveal the presence of a wormhole. S2 is the closest star to the likely location of the black hole, Sagittarius A star. The idea is to identify all the different influences on S2's orbit, to see if something unknown affects the way the star moves through space. Astronomers think that the main influence on S2's orbit is the huge gravity of Sagittarius A star. But S2 moves in a very crowded corner of space, where other stars and black holes could affect its motion. Astronomers are studying the effects of all these objects to calculate the path of S2 with extreme accuracy. They're looking for a tiny deviation that they can't explain, which could be gravity leaking through a wormhole. The theory sounds fantastical, but physics supports it as a potential way to identify the presence of a wormhole. Collisions between massive objects like neutron stars and black holes generate gravitational disturbances. These huge distortions in space-time are the one thing that could potentially pass into white holes. In theory, a disturbance from a violent event at the other end of the universe might enter a nearby black or white hole, travel through a wormhole, and emerge from Sagittarius A star. This disturbance from an unknown time and place could then alter the orbit of the star S2.
What if we could better and better observations over time and look very carefully at the way the star is accelerating, we might be able to just tease tiny little clues out of the orbit that there's something else in there, some more gravitational exotic things, perhaps even a wormhole.
Future telescopes will be able to track S2's movements with greater precision. If they do spot something unusual, Einstein's incredible wormhole theory could be proven correct.
If we find out that wormholes actually do exist, and there's one in our stellar neighborhood, then this opens up a whole new realm of research. This tells us that we can now understand space and time in ways that we never could have before. So even though humans may not be able to go at any time in the near future, we could start along the path and send probes to see what happens.
White holes are one of the weirdest ideas in science. They could be responsible for unexplained blasts of radiation that shoot across our universe. It is possible that they are born at the moment super ancient black holes die. What started as an idea, triggered by the mind of the world's most famous physicist, could really exist.
If Einstein turned out to be right about white holes, man, I would just say, there he is again. He did it again, Albert Einstein, right? My hero.
In the future, we could discover a real white hole that is a portal to a different time and space.
All of a sudden access not only all the space of the universe, but the entire history and future of the universe as well. And from there, your imagination can take you pretty much anywhere.
New telescopes promise to unlock the mysteries of these cosmic wonders. White holes could exist, and they could be out there, just waiting to be discovered.